When we're studying waves, there are various quantities relating to the wave that we can measure, and the main ones are listed here. So we have the wavelength, the amplitude, the time period of the wave, the frequency of the wave, and its speed. And I'm going to just very quickly define each one and show you what each one represents on a wave and how to measure them. Okay, so let's start with the wavelength because that's kind of like the easy one. So the wavelength is simply the distance from one crest on the wave to the next. So we have here a little diagram of a transverse wave and one of a longitudinal wave with the wavelength noted on that diagram. So it's the distance from this point here to this point here. And when you're measuring, you have to be really precise. You know, this is not right. This is not the wavelength. That's different. You have to be sure to show that you're going from one peak exactly to the next peak. It's also the difference it's also the distance between two troughs. It's also the distance between the rest point of the wave on its way down to the next rest point of the wave on its way down. All those distances are the same and they all represent one wavelength. In a longitudinal wave, the way to measure it is from the center of one compression to the center of the next compression. You could also measure it from the center of one rarefaction to the center of another rarefaction. So again, those are all the same distance, so those all represent one wavelength. But effectively, it's the distance from one crest on the wave, or one peak, or one point on the wave to the next successive point at the same state of the wave, if you like. Okay, so that's the wavelength, nice and easy. The amplitude, there are various different ways to measure an amplitude, but the main way to measure an amplitude and the way we need to know how to measure it is as follows. The amplitude of a wave is the maximum disturbance from the 0 point, i.e. the distance from the center line of the wave upwards or downwards to the peak. So it's effectively the distance measured from the middle to the top, and that is what we call the amplitude. So it's half of what we call the peak to peak. So the peak to peak would be all the way from the trough to the crest, but we want to measure the amplitude in this way, from the center line, from the rest position or the 0 point where the material would be if there were no wave, to the crest of the wave. The maximum distance away from the center line, and that's what's known as the amplitude. The next one is the time period of the wave. So the time period is measured in seconds and is defined as the time it takes for one complete cycle or oscillation of the wave. So it's how long it takes from, it's difficult on this diagram because this is a diagram against time, so we really need to see a moving one, which we'll look at in a minute. So imagine you're sitting at this point here on the harbour, and there's the harbour wall, and there are waves passing through you, and they're going past you like that. If you had a little stopwatch, you could time when this one was parallel with you, would level with you, and then when this one was parallel with you. And the difference in the time as they move through would be the time period. So it's the time it takes for one complete wave to pass a particular point, one complete cycle or oscillation. The frequency is how many complete waves, the number of complete waves that pass a point per second. So this is related to per second rather than seconds. And because it's per second, it's the number per second rather than the number of seconds, it's the inverse of the time period. So we can use this equation here to calculate frequency. Frequency is 1 divided by the time period, or the inverse of the time period, the reciprocal of the time period, 1 over the time period. So for example, if the time period was 2 seconds, then the frequency would be 1 over 2, which is 0.5. And the unit of frequency is the hertz, which is shortened to capital H, Z. So the hertz is the measurement of frequency. Okay, so that's frequency. And then we have the wave speed or the wave velocity, and the wave speed, wave velocity is calculated by using an equation. And it can be calculated this way, and this is often the way we do it. So the wave velocity or the speed is equal to the frequency, that's the number of oscillations per second, multiplied by the wavelength. Frequency times wavelength. And in terms of units, velocity is in its usual units of meters per second when the frequency is measured in hertz and the wavelength is measured in meters. We shorten that to this in symbols. Now there's a funny little Greek symbol in here, and it's this one in the end here. This symbol here, which is a bit like an upside down Y, if you haven't seen it before, is called lambda. Lambda. It's a Greek letter L and is the symbol for wavelength. So quite often we just write a lambda sign rather than writing out wavelength. Okay, so V equals F lambda. V is the velocity, F is the frequency, and lambda is the wavelength. And that's how we measure waves. So here I'm using the PhET animation to demonstrate those quantities that we can measure about waves. So some of them require the wave to be moving, and here's a wave just oscillating on a string, and we can see that it's a transverse wave. And some of them require the wave to be stationary so that we can get a little snapshot of it. And the first two we're going to measure using a snapshot of the wave. So the first one is the wavelength. So the wavelength is the distance from one peak to the next, and we can see that it's about 4.1 centimeters. So we're measuring from the top of that peak to the top of the next peak. So that's about 4.1 centimeters. The amplitude as well is the distance from the center line to the top, from the rest position to the maximum displacement or maximum disturbance. So that's there. That's just below 0.8. Let's say it's 0.75. So that's the amplitude. So the wavelength and the amplitude can be measured in this way. To measure the time period, though, we need to set the wave moving. So let's set the wave moving. There we go. And let's have a marker point, because the time period is the time taken for one complete oscillation of the wave. So we're going to use this green dot here on the edge of the ruler, on the left-hand edge, to measure the time period. So when the dot gets to the top, I'm going to start the stopwatch down in the corner there, and when the wave gets to the top again, I'm going to stop it. So we can see there it was about 2/3 of a second, 0.65 seconds on my reckoning. So that's the time period, the time it takes for one complete oscillation of the wave. Now the frequency is how many waves pass a particular point per second. So we would time it for 1 second and see how many waves have passed the point in that particular time. So let's do that. Let's time for 1 second. I'll start it at the top. Go. So that's one complete wave and a half. So the frequency is about 1.5 hertz. And actually that's what it says down on the dials on the bottom. We can see that we have worked that out correctly. So 1.5 waves pass a particular point per second. That's frequency, 1.5 hertz. And those are the ways we can measure the wave. The speed is equal to the frequency times the wavelength. So if we were going to measure the wave's speed, we would measure its wavelength, which is just over 4 centimeters, convert that to meters, and then multiply it by the 1.5 frequency, and that would tell us how fast the wave is traveling from left to right.